This two-part video focuses on the high voltage power diodes and will highlight the superior characteristics of wide band gap, especially silicon carbide diodes for the high voltage applications. Part 1, we will start with the conventional silicon based high voltage so-called PIN diodes. Outline: I will give a very brief overview of the basic PN junction diode operation to understand the requirements and mainly the trade-offs involved among the reverse blocking voltage, the on-state resistance, and the reverse recovery of the diodes. That will lead into the discussions on the conventional high voltage silicon based PIN diodes along with some numerical values of critical parameters from data sheets. And then in part 2 we will look at the operation of Schottky diodes, explain why high voltage silicon Schottky diodes are not practical and how silicon carbide Schottky diodes can outperform even the silicon based PIN diodes. Then we will look at some numerical examples from data sheets comparing the for the same specification silicon PIN diodes versus the silicon carbide Schottky diodes. A diode obviously is a major semiconductor component in all power electronic converters. For example, this diode in the boost converter that we saw in an earlier video, or as freewheeling diodes across another control switch, and many such applications. Diode is essentially a passive uncontrolled switch, meaning its turn on and turn off are determined not by a gate control but rather by the circuit operating conditions, mainly by the turn on and turn off of a different switch in the circuit. The diode non-idealities cause the conduction loss and the switching loss. The conduction loss of course depends on the non-zero forward voltage drop, and the switching losses, the turn-on losses are negligible with the small forward recovery, whereas the during turn-off the diode current actually goes negative for a short interval during the reverse recovery process, and this can represent a significant source of power loss. These are simulation waveforms using a very detailed model of a diode. Somewhere at this instant a MOSFET was turned on, so in response the diode current comes down with a finite slope, reaches zero but also continues to fall to a large negative value as shown here. At this instant the diode voltage also begins to rise rapidly towards its final blocking voltage magnitude, and the product of this high voltage and this high reverse current causes large instantaneous and therefore large average power loss as well. So it's not just the switching power loss in the diode. The reverse recovery current, this large negative current, also results in higher than the normal current at the MOSFET at the instant of its turn on, adding to the turn on switching losses of the MOSFET as well. Let's quickly review the basic operation of a PN junction diode, which is formed by bringing together a p-type or a p-doped silicon material with an n-type silicon material. So on the n side, the electrons are the majority carriers. It has excess electrons, and these electrons diffuse from this higher concentration region towards the junction and into the p-type material where they have low concentration. In the process, they leave behind these positively ionized atoms near the junction. On the p side, it has excess holes. The holes are the majority carriers here. So once again, the holes diffuse from this region of higher concentration towards the n region, and in the process they also leave behind now a negatively ionized atoms near the junction. So this region where you have this positive and negative ionized atoms, it is called as the depletion layer or the space charge layer. So the presence of these charged ionized atoms, positive on this side and negative here, creates an electric field and therefore a potential with a positive voltage on the n side and negative on the p side. And this voltage prevents in equilibrium further diffusion of electrons and holes across the junction. Now let's look at this situation first. So this is when you apply a negative voltage across the diode, meaning a positive voltage on the N side and a negative voltage on the P side. So under this condition, as you can see in the figure, the depletion region becomes larger, and this entire voltage, reverse voltage, is blocked by the depletion layer. Now for forward bias conditions, we apply a positive voltage on the P side and the negative voltage on the N side. So this results in the depletion layer becoming narrower, and due to this, there's no longer enough barrier for the diffusion of the electrons and holes. So the electrons now diffuse from the N region towards the P region, conducting current, and similarly the holes from the P region also diffuse into the N region, also contributing to the net current. So in the process, what we do have are a large number of minority carrier electrons on the P side, and similarly a large number of minority carrier holes on the N side. So therefore, to turn off the diode, these minority carriers, the holes on the N side and the electrons on the P side, they have to be removed by hole electron recombination or otherwise. The stored minority carrier charge on either side and the time it takes to remove them, they significantly influence the switching times and therefore the switching losses. Okay, let's analyze the off state of the diode to better understand the reverse blocking voltage capabilities. So we'll consider a symmetrical PN junction, meaning the doping concentration on the P and the N sides are equal. So we apply the reverse bias as shown, and this results in this large depletion region of width or length WD, and because of the similar doping concentration, the width on the P side and the width of the depletion layer on the N side, they are equal, WdP and WdN. Now these ionized atoms, the positive on the N side and the negative on the P side, they create this electric field, and the electric field is given by the Gauss's law, which says the gradient of the electric field is the charge enclosed over epsilon. And for the one-dimensional case here, where the x is in the direction of the depletion with WD, then the Gauss's law is given by dou over dou x of E is q over this epsilon. So then we can get the electric field as a solution to this one-dimensional Gauss equation, and is plotted as shown here. So clearly from the plot we can see that the electric field is maximum right at the junction, and it is 0 on both the edges of the depletion region. Now looking at the N side of the junction, the total charge here is the product of the doping concentration given in the number of donor atoms in the case of N type per unit volume times the charge of an electron. So that's the total charge, and then substituting that for the charge in this partial differential equation, we get an expression for the peak value of the electric field as shown here. It's simply ER over this WdN is the total charge over epsilon. So then the potential difference or the voltage across this entire depletion layer, which is also essentially the total blocking voltage of the diode. So that is given by the integral of the electric field, which is the area under this triangle. So that would be 1/2 times this ER, which is the peak electric field, times the total width of the depletion layer. So therefore the maximum electric field for the material, the critical electric field for the material, and the width of the depletion layer together determine the maximum reverse voltage that can be applied to the diode. So the analysis can be extended to the asymmetrical PN junction shown on the right. So here the doping concentration on the N side and the P side are very different. So in this case, for example, if you consider a P plus and an N minus junction, then the depletion region actually extends more into the lightly doped N side rather than the P plus side. And in the extreme case where we have the P region to be significantly more heavily doped than the N region, then the entire WD is equal to just the WDN, the one on the N side of the junction. Then the maximum value of the electric field happening at the junction is given by this expression, which is exactly the same as what we derived in an earlier slide, except that for this extreme case we replace WDN by the entire WD. So that gives us an expression for the width of the depletion region in terms of the electric field and the doping concentration. And the reverse blocking voltage VR is given by, we derived earlier, 1/2 times WD times ER. So we just need to multiply this by ER over 2 to result in this expression for the reverse voltage for the diode. So in this equation for the voltage, clearly the ER, that depends on the critical, the breakdown strength E critical of the particular semiconductor material. Also note that the E critical also depends to a very small degree on the doping concentration ND, but that, as seen by this expression, is quite negligible. So with that, we can say that the maximum reverse voltage or the breakdown voltage rating of a diode VBR is actually inversely proportional to the doping concentration for a given semiconductor material. Or lower the doping concentration, higher is the reverse blocking voltage. So we can use this expression to determine what should be the required doping concentration to achieve a required voltage rating. Okay, so lower ND surely can result in higher voltage breakdown voltage rating, but lower doping concentration also means poor conductivity, or in other words, higher on-state resistance for the diode. So because the resistivity for the N-type region is given by 1 over the charge of an electron and the mobility of electron and the doping concentration. So lower the ND, higher is the resistivity and the resistance of the diode. So clearly higher blocking voltage is achieved at the expense of increased on-state resistance, and that is the main problem with the conventional silicon PN diodes. Now, high voltage silicon diodes, they tried different structures and different design trade-offs in solving this problem. Most of the high voltage silicon diodes have the so-called PIN structure. So this consists of a lightly doped N minus region between a heavily doped P plus and an N plus regions. So the lightly doped N minus region, its doping level is so small that it is closer to the intrinsic silicon material itself, and that's what gives this configuration the name PIN, where I stands for intrinsic. So then the entire drift region is this N minus region, and so this figure actually corresponds to one type called the punch through diode type, where the depletion layer actually extends throughout the entire drift region. So we can go through a similar analysis as we did in the previous slides and show that the breakdown voltage is given by this expression for the PIN diode structure. So this we can design for a given breakdown voltage rating by appropriate choice of the width WD, which in this case is the width of the N minus region mostly. But the question is, does that significantly affect the on-state resistance? The lightly doped N minus region certainly significantly contributes to the on-state resistance of the diode. However, this phenomenon called conductivity modulation helps to reduce the on-state resistance in this drift region. So because now we have a P plus and N minus junction, so the large number of holes are injected into this N minus region, and that's because of this larger concentration difference. And some of these holes that is injected into the N minus region, they recombine with the electrons in the N minus region, but some of them also attract more electrons from the N plus region, and that so the lightly doped drift region actually ends up having a high concentration of charge carriers, and therefore that reduces the on-state resistance significantly. But however, the main problem here is we have now a large number of minority charge in the drift region, and so that results in longer reverse recovery time and larger reverse recovery charge. So the design is once again a trade-off between the on-state resistance and the switching characteristics, the reverse recovery characteristics. So we can by design reduce the reverse recovery time by reducing or controlling this minority carrier lifetime. And this will enable faster recombination of the minority carriers, therefore reducing the reverse recovery time. For the N-type drift region, as the one that we are considering here, the holes from the P plus region, those are the minority carriers, and the recombination will be faster if more electrons are available. So that's if more donor atoms are present. And this can be achieved by the process as indicated here. But the net result is that they still end up increasing the on-state voltage drop. The nature of the reverse recovery characteristics can also be controlled by the design and the structure. So for example, the punch-through structure, where the depletion layer shown by this purple box completely covers the N- region. So that will result in an abrupt fast reverse recovery as shown by this sharp snap back to zero current from this large reverse recovery peak, versus a non-punch through arrangement where the depletion layer, again this purple box, does not extend to the over the entire N- region. So this can result in a softer but slightly longer reverse recovery process as shown here, and both have their applications. But the key point is that the on-state drop and recovery time are competing requirements for the silicon pin diodes, and that involves a careful trade-off. So in the last couple of slides, I wanted to highlight the characteristics of a typical state-of-the-art silicon pin diode in terms of its forward drop and reverse recovery characteristics. So this is a diode rated for an average current of 30 amps and a peak voltage rating of 1200 volts. And this plot shows the forward voltage drop. So these are typical values. So for example, at a junction temperature of 150 degrees C for 30 amperes, it's about 1.8 volts versus around 25 degrees C. At 25 degrees C junction temperature, it is closer to 3 volts forward drop. So this plot shows the maximum values for the same forward voltage drop as a function of the current, and here it is significantly higher. So at 150 degrees C junction temperature, for the same current 30 amperes, we would have a forward drop of more than 2.6 volts, and at 25 degrees C it is significantly higher at close to 4 volts for the rated 30 amperes current. So in the part 2 of the video, we'll be comparing all of this with the silicon carbide Schottky diodes and see how it significantly outperforms these pin diodes. These plots show the reverse recovery characteristics for this pin diode. So the one on the left is the peak reverse recovery current, and on the right is the reverse recovery time, and both of them are plotted versus this rate of change of forward current, how fast the forward current comes down during the turn off transition, and that is decided more by the external conditions. So assuming a typical value of about 200 amperes per microsecond, the peak reverse current is about 17.5 amperes. Okay? So this is for a forward current rating of 30 amperes, and these plots are given at a reverse blocking voltage of half the rated value, 600 volts. And then looking at the reverse recovery time, again for the same DIF over dt, the reverse recovery time is closer to about 280 nanoseconds, which is actually quite high for high frequency converters. So in conclusion, we can say that the design of these silicon pin diodes is really a trade-off between the on-state drop, the reverse recovery characteristics. So in the next part of the video, we will look at the silicon carbide Schottky diodes and understand how they achieve this better performance.